Important theorem on modulus and argument. Let Z1 and Z2 belongs to C. That is, these are two complex numbers. Then prove that mod Z1 into Z2 is mod Z1 into mod Z2, and argument of Z1 into Z2 is argument of Z1 plus argument of Z2. So conversion of multiplication into addition, and mod Z1 by Z2 is mod Z1 divided by mod Z2, where Z2 is not obviously 0. And argument of Z1 by Z2 is what? Argument of Z1 minus argument of Z2. That is the conversion of division to subtraction and conversion of multiplication to addition. This argument is behave like a logarithmic function. We know that log a plus b is what? Log a into b is what? Log a plus log b. And log a by b is what? Log a minus log b. That is, this argument behave like logarithmic function, log function. Okay, so we have to prove this a and b, theorem a and b. So this theorem is important as far as exam concerned. So let mod z1 is equal to r1, and argument of z1 is theta1. We assume this, and modulus of z2 is suppose r2, and argument of z2 is theta2, and therefore the polar form z1 is what? R1 in bracket cos theta1 plus I sin theta1. This is the polar form of z1, and polar form of z2 is what? R2 cos theta2 plus I sin theta2. So these are the two complex numbers. Then the proof of first A, that is first find z1 into z2. Z1 is this and z2 is this. So r1 into r2 is simple multiplication, and multiplication of these two bracket. We have four terms: cos theta1, cos theta2, then cos theta, this sin theta1, I sin theta1, cos theta2. Okay, the last term cos theta1, I sin theta2. This is cos theta1, I sin theta2, and then I sin theta1, cos theta2, and last term is what? I square sin theta1, sin theta2. So write first that step, and then substitute I square as -1, and then cos theta1, cos theta2 minus sin theta1, sin theta2 in one bracket, and plus the remaining two terms, that is cos theta1, sin theta2. This is the cos theta1, sin theta2. I take I coefficient common, and this I as sin theta1, cos theta2, sin theta1, cos theta2. Take I as common. So write one more step, that first write multiplication of these two brackets. Multiplication of these two brackets. We have four terms. What are that? Cos theta1, cos theta2 plus I sin cos theta1, sin theta2, I, and then I sin theta1, cos theta2, and the last term is what? I square sin theta1, sin theta2, and then write I square as -1. We have this as a real part, and this is the imaginary part, that is the coefficient of I. Remaining two terms, take I as a common factor. So this is the z1 into z2, and therefore z1 into z2 is r1 into r2 cos theta1, cos theta2 minus sin theta1, sin theta2 is cos theta1 plus theta2, because we know that cos a plus b is what? Cos a cos b minus sin a sin b, and this is the expansion of this sin theta1 plus theta2, because what is sin a plus b is sin a cos b, sin a cos b plus cos a sin b. This is the expansion of this sin theta1 plus theta2, all right? Sin theta2 plus theta1. So this indicates that modulus of z1 into z2 is r1 into r2, because we have this z1 into z2 in the polar form. This is the modulus. That is, if we write z1 as r1 into cos theta1 plus sin theta1, what does this indicate? That r1 is modulus of z1 and theta1 is argument of z2. Like that, z1 into z2 expressed in this form, r1 into r2 in bracket cos theta1 plus theta2 plus I sin theta1 plus theta2. That is, this is the polar form of this number, z1 into z2, and this indicates that modulus of z1 into z2 is r1 into r2, and argument of z1 into z2 is theta1 plus theta2. Like this. If you write z2 as r2 cos theta2 plus I sin theta2, what does this indicate? That r2 is modulus of z2 and theta2 is argument of z2. So z1, we have z1 into z2 is in this form, means r1 into r2 is modulus of z1 into z2, and theta1 plus theta2 is argument of z1 into z2. And what is theta1? Theta1 is argument of z1. Theta1 is argument of z1. plus theta 2 is argument of Z2. Theta 2 is argument of Z2. And therefore we have that mod Z1 into Z2 is R1 into R2. What is R1? R1 is mod Z1. And what is R2? R2 is mod Z2, and that is modulus of Z2. And therefore what we have, modulus of Z1 into Z2 is modulus of Z1 into modulus of Z2, and argument of Z1 into Z2 is argument of Z1 plus argument of Z2. And that is we have to prove. Then proof of B. So similar to this Z1 into Z2, consider Z1 by Z2. Find Z1 by Z2. So Z1 is R1 cos theta 1 plus I sin theta 1. Z2 is R2 cos theta 2 plus I sin theta 2. Now we have to find its division of these two complex numbers, means rationalizing denominator. How we can find the division of two complex number? By rationalizing denominator or by multiplying conjugate factor of denominator. So cos theta 1 plus I sin theta 2, its conjugate factor is cos theta 1 minus I sin theta 2. So multiply and divide by the same factor. Then the multiplication of these two terms, we have four terms. What are that? Cos theta 1, cos theta 2, then plus, not plus, minus I cos theta 1 sin theta 2, then plus I sin theta 1 cos theta 2, and last term is minus I square sin theta 1 sin theta 2. Then write minus that I square as minus 1. Then we have cos theta 1 cos theta 2 plus sin theta 1 sin theta 2 as in one bracket. So write first that four terms and then write this step. And we have the imaginary parts that I take I as common. So what is that? Sin theta 1 cos theta 2 and cos theta 1 sin theta 2 minus term, okay, minus cos theta 1 sin theta 2. So and the denominator is what? A, this is A, this is B, suppose. So A plus B into A minus B is A square minus B square. Okay, that is cos square theta 2 minus I square sin square theta. What is I square then? Minus 1. So minus minus plus 1. That is denominator is what? Cos square theta 2 plus sin square theta 2, and it is equal to 1. So we have this side. Or either write the multiplication of these two brackets. We have four terms. What are that? Cos theta 2 into cos theta 2. That is what? Cos square theta 2. And then minus I cos theta 2 sin theta 2 and plus I sin theta 2 cos theta 2 become 0. And last term is what? This term is plus, this term is minus. So minus I square sin square theta 2 means plus sin square theta 2. So that is 1. And then this is the expansion of cos theta 1 minus theta 2. Because what is cos A minus B? Is cos A cos B plus sin A sin B. And this is the expansion of what? Sin theta 1 minus theta 2. What is sin theta 1 minus theta 2? Sin A minus B is what? Sin A cos B minus cos A sin B. And this equation, that is, we have the value of Z1 by Z2 is in this form. That is, this is the polar form of this Z1 by Z2. And what this indicates? That R1 by R2 is modulus of this number. That is, modulus of Z1 by Z2 is what? R1 by R2. And what is R1? R1 is modulus of Z1, R2 is modulus of Z2. And theta 1 minus theta 2 is argument of Z1 by Z2. Argument of Z1 by Z2 is what? Theta 1 minus theta 2. That is argument of Z1. Theta 1 is argument of Z1, theta 2 is argument of Z2. And that is, we have mod Z1 by Z2 is mod Z1 divided by mod Z2. And argument of Z1 by Z2 is what? Argument of Z1 minus argument of Z2. So this is important theorem. And then next note, argument of Z cube. For example, we find argument of Z. What is Z cube? Z into Z into Z. And by using this theorem, that argument of Z1 into Z2 is argument of Z1 plus argument of Z2. If we find argument of Z1 into Z2 into Z3, then what is it? It is argument of Z1 plus argument of Z2 plus argument of Z3. That is, if we can find argument of Z1 into Z2 into Z3 up to Z10, then it is what? Addition of argument of Z1 plus argument of Z2 plus argument of Z3. In this way, argument of Z10. So what is argument of Z1? Z into Z into Z. Z cube is Z into Z into Z. Is argument of Z plus argument of Z plus argument of Z. Conversion of multiplication to addition. And that is 3 times argument of Z. That is argument of z cube is 3 times argument of z. In this fashion, if I find argument of z raised to n, then it is n argument of z. Similar to logarithmic function. What is log of z? Log of a raised to n is n into log, like that. So this argument behave like a logarithmic function. Then find the principal argument of the following complex number. This is the complex number, and this is the complex number. So how you can find I divided by minus 2I? Simplify this first. That is multiply by minus 2 plus 2I divided by minus 2 plus 2I. That is rationalized denominator, and express this number in the form x plus iy, x plus iy, and then find its modulus and argument. This is the procedure that's applied in the previous examples. These are the previous examples. That is, we go to find the argument of 1 by 1 plus I, then rationalize that, that is rationalize denominator, and convert that number in the form x plus iy. Okay, and then find its modulus and argument. This is the previous method. We can also apply the method for this example, or we can use now this theorem. That is, argument of z1 into z2 is argument of z1 plus z2, and argument of z1 by z2 is argument of z1 minus argument of z2. So we can also use we have to find the principal argument only. We have to find principal argument. If I have to find modulus, then convert this number to the number convert to x plus iy form. So in order to find principal argument, no need to convert this number in the form of x plus yi. So what is the argument of this I by minus 2I? Is argument of z1 by z2 is what? Argument of z1 minus argument of this z2. So by using that theorem, argument of z1 by z2 is argument of z1, that is argument of numerator minus argument of denominator. And argument of I is pi by 2, and argument of minus 2I is minus 3 pi by 4. 3 pi by 4 by using how we can find the argument and modulus? By using these formulas. That is, use these 4 formulas. Okay, argument of I and argument of that minus 2I. Okay, so we have this, and then argument of minus I minus argument of minus 2I, that is this side, is equal to pi by 2. That is the argument of I minus 3 pi by 4, minus 3 pi by 4, that is plus 3 pi by 4. 4 is the LCM, and 2 plus 3 is 5 pi by 4. So this is the another method, or express this number in the form x plus yi, and then find its modulus and principal argument. Obviously, principal argument is lies between 180 minus 180 to 180. So we have this is minus 3 pi by 4 by subtracting 2 pi, and then the argument of this root 3 minus I raised to 6 is what? Suppose this is z number, then its modulus is what? 6 argument of 6 into argument of root 3 minus I. By using this argument of z raised to n is n into argument of z. So argument of z raised to 6 is what? 6 into argument of z, and argument of root 3 minus I is minus pi by 6. So argument of this number is what? 6 into minus pi by 6 is minus pi. So actually it is plus pi, because this is not in the range minus 180 to 180. So strictly greater than minus 180. So minus pi means pi. So this is the method. But don't use these methods to find principal argument and argument. Use solve these problems by previous methods. That is, convert these numbers in the form of what? X plus yi. Find 6 power, and then solve this example. Don't use this method. It is just for application of theorem. It is just for application of theorem. This problem. Don't use these methods for problems. So this is just for application. What are the applications of the previous theorem? Then next theorem is also important. It's called triangle inequality. So Z1 and Z2 are complex number. Then prove that mod Z1 plus Z2 is less than or equal to mod Z1 plus mod Z2. It's called triangle inequality. Well, already this is uh, you observe this for a real number, that mod a plus b is less than or equal to mod a plus mod b. Like that, mod z1 plus z2, z1 and z2 are complex numbers, is less than or equal to mod z1 plus mod z2. So consider mod z1 plus z2 bracket square, and mod z square is z into z bar. So this is z1 plus z2 into z1 plus z2 bar, and we know that a bar, a plus b bar is what? A bar plus b bar. So z1 bar plus z2 bar, and the multiplication of these two bracket, we have four terms: z1 into z1 bar, z1 into z2 bar, then z2 into z1 bar, and z2 into z2 bar. We have four terms. And z1 into z1 bar, again by using this, z into z bar is mod z square. Like that, mod z1 into z1 bar is mod z1 square, plus this is z1 into z2 bar, and we write this as z2 into z1 bar as z1 z2 bar bar. What is the z bar? Is itself z. No, don't write here z2, itself z. Z bar is what? Z bar. So what is the z1 into z2 bar? If you simplify this, then what we have? Z1 bar, because a into b bar is what? A bar into b bar. So z1 bar, if you simplify this quantity, then what we have? Z1 bar, that is this quantity. Z2 bar bar, that is z2. That is, this is the value of this. Then plus z2 into z2 bar, by using this, z into z bar is mod z square. So this is mod z2 square. Then mod z1 square is 2 time real part of z1 into z2 bar, because z plus z bar is equal to 2 time real part of z. So this is, suppose this is z and this is z bar. So this is what? Suppose this is z, z1 into z2 bar. The same quantity is here, z1 into z2 bar bar. That is we have, by using this concept, 2 time real part of z1 into z2 bar. And all these remarks, all these remarks are after we observe after the definition of modulus and argument. What are the properties of that modulus? These are the properties that z bar is what? Modulus of z bar and modulus of z both are same. Mod z square is z into z bar. Okay, and mod z is greater than or equal to real part of z. Okay, and z plus z bar. Okay, so all these remarks. So it's 2 time real part of z. Okay, z plus z bar is 2 time real part of z. Z plus z bar. If we add z and z bar, then what do we have? Z plus z bar. Z is x plus yi, and z bar is what? X minus yi. Then its addition is what? 2x. That is 2x means 2 time real part of z. So z plus z bar is 2 time real part of z. So that remark here, z plus z bar is very obvious, that z is x plus yi, then z bar is x minus yi, and then addition is 2x, that is 2 time real part of z. X means real part of z. So by using that remark, then it is less than or equal to, real part of z is always less than or equal to mod z. Here is, we observe this, that real part of z is always less than or equal to, real part of z is less than or equal to mod z. Imaginary part is also less than or equal to mod z. So we have here sign less than or equal to. Here the sign we have less than or equal to. Don't write equal to sign, because real part of z into z1 into z2 bar is replaced by mod z1 into z2 bar. And this is the relation, that is real part of z. Suppose this is z. So real part of z is what? Is less than or equal to mod of this, mod of z. Okay. Then mod z1 square, 2 times separate the mod, because mod a into b is mod a into mod b is equal to mod z1 z2 square. Then use the a of theorem 4, that is mod z1 into z2, that is this, mod z1 into z2 is mod z1 into mod z2. So by using that part, this is separate the modulus. We have equal to side. Then equal to 2 times mod Z1 into mod Z2 bar, because mod Z2 bar and mod Z2 both are same. Mod Z bar and mod Z both are same. So mod Z2 bar is replaced by mod Z2, and this is the square of this bracket, mod Z1 plus mod Z2 bracket square, because a plus b square is what? A square plus 2 times a into b plus b square, and taking root of both sides. So we have mod Z1 plus Z2 square is less than or equal to, here is the less than or equal to this. So what we have, mod Z1 plus Z2 square is less than or equal to mod Z1 plus mod Z2 bracket square, taking positive square root of both sides, taking root of both sides. Then we have mod Z1 plus Z2 is less than or equal to mod Z1 plus mod Z2. The square get cancelled, and this is the proof. So this is very important theorem. Then what is modulus of Z1 minus Z2? Is what? Is modulus is less than or equal to modulus. Suppose we write this Z1 minus Z2 as Z1 plus in bracket minus Z2, and then apply the previous theorem that mod Z1 mod A plus B is less than or equal to mod A plus mod B. So consider this Z1 as A plus minus Z2 as B. So is less than or equal to mod Z1 plus mod Z2. So write one more step here, write equal to, here write equal to, and then write is equal to mod Z1 plus in bracket minus Z2, and then apply previous theorem. We have mod is less than or equal to mod Z1 plus mod of minus Z2, and mod of minus Z2 is mod of Z2. Mod of minus Z2 and mod of Z2 both are same, and therefore we have mod Z1 minus Z2 is less than or equal to mod Z1 plus mod Z2. So mod Z1 plus Z2 is less than or equal to mod Z1 plus mod Z2, and mod Z1 minus Z2 is also less than or equal to mod Z1 plus mod Z2. Don't write here minus sign. Mod Z1 minus Z2 is not less than or equal to mod Z1 minus mod Z2, but mod Z1 minus Z2 is less than or equal to mod Z1 plus mod Z2, and therefore if we compare these two, combine these two, then we have this, that mod Z1 plus or minus Z2 is less than or equal to mod Z1 mod Z2. If we this is the example that prove that this, that mod Z1 plus minus Z2 is less than or equal to mod Z1 plus mod Z2, then prove first this, then prove this, and then we write that from 1 and 2 we have this. And we generalize this inequality that mod Z1 plus Z2 plus Z3 plus Zn is less than or equal to mod Z1 plus mod Z2, in this way mod Zn. The next example is also important, theorem is also important. For any Z1 and Z2 belongs to C, that is Z1 and Z2 are complex number, prove that mod Z1 minus Z2 is greater than or equal to mod modulus of mod Z1 minus mod Z2. So what we have to prove? Modulus of Z1 minus Z2 is greater than or equal to modulus of Z1 minus modulus of Z2. So interchange the sides. That is, we have to show this is less than or equal to this. Change the sign. Change the interchange the sides. That is right side as a left side and left side as a right side. Then we have less than or equal to sign here. And we know that when mod Z is less than or equal to C, if and only if Z is less than or equal to C and greater than or equal to minus C. This is the property of modulus. And this is this proof of this property is in the theorem in the paper number 2, that is calculus paper, that mod Z is less than or equal to C if and only Z is less than or equal to C and greater than or equal to minus C. That is where, suppose this is this quantity mod Z1 minus mod Z2 as a Z, consider as a Z, this quantity as a Z, and this total quantity that is mod Z1 minus Z2, this total quantity as a C. Then what we have, minus C, that is minus of this, minus mod Z1 minus Z2 is less than or equal to, this is the Z, this mod Z1 minus Z2. Z is what? This mod Z1 minus mod Z2 is less than or equal to C plus C. This is the C quantity, mod Z1 minus Z2. That is, in order to show this, we have to show this. Then we show this in two parts. First, we show this is mod Z1 minus Z2 is less than or equal to mod Z1 minus Z2. We show this first, and then we show this is the second. And so combining 1 and 2, we have this, and then we have this. So start the proof of this, that we have to show mod Z1 minus mod Z2 is less than or equal to mod Z1 minus Z2. So start with mod Z1 is equal to mod Z1 minus Z2, subtract Z2 and add Z2. And then this as considered as this is one complex number, and this is other. Suppose this is A and this is B. Then A mod A plus B is less than or equal to mod A plus mod B by triangle inequality. And then shift this mod Z2 in LHS. So what we have, mod Z1 minus mod Z1 minus mod Z2, this shifting quantity, is less than or equal to mod Z1 minus Z2. And then we have this part, that mod Z1 minus mod Z2 is less than or equal to mod Z1 minus Z2. This is suppose first. Then we have to show this part, So start with mod Z1 minus Z2 is what? Mod Z2 minus Z1, because mod of Z and mod of minus Z both are same. So these two are same. Mod Z1 minus Z2 and mod Z2 minus Z1 are same. And this is greater than or equal to, this is greater than or equal to mod Z2 minus mod Z1 by using this. That is Z1 minus mod Z2 minus Z1 minus Z2 is what? Greater than or equal to mod Z1 minus mod Z2. So by using this, so Z2 mod Z2 minus Z1 is greater than or equal to mod Z2 minus mod Z1 by using this, by using 1. And then we have this mod Z1 minus Z2 is greater than or equal to, take minus sign from common from this side, minus in bracket mod Z1 minus Z2. And therefore we have this, that minus, shift the minus sign here, that is change the sides sign of both sides, and then greater than or equal to convert to less than or equal to. If we change the signs of both sides, then we have the reverse sign, that is this is what? Minus mod Z1 minus Z2 is less than or equal to, greater than or equal to, converted to less than or equal to, minus become plus mod Z1 minus Z2. So this is the proof of this part. Or similar to this proof, number 1 proof, we can prove the second one also. That is, consider we have mod Z2 is equal to mod Z2 minus Z1 plus Z1, and then write the proof. We have this. So by using 1 and 2, what we have? We have combining 1 and 2. We have this minus mod Z1 minus Z2 is less than or equal to mod Z1 minus Z2, and is less than or equal to mod Z1 minus Z2 is less than or equal to mod Z1 minus Z2. And therefore this implies this is proof, and therefore this is proof, that mod Z1, the mod of this is less than or equal to this. Okay, by using this inequality, that is x is less than or equal to a if and only if x is less than or equal to a and greater than or equal to minus a. Mod x is less than or equal to a. This is the, and this proves the theorem. That is, we have to show this means this. So we'll see the remaining examples in the next lecture. We'll see the remaining examples in the next lecture.